Alrighty. Hey, Katie, what can I do for you?
I have a question on the homework again.
Sure.
It's number 15 on homework 5.
Okay, let me see here. Turn this on. All right, so on number 15. Ah, yeah, this is fun. So this is going to come from one of our special trig limits. That's the idea. We need to use, remember those, we've got these two special trig limits. The limit as, I'll use x, limit as x goes to 0, sine x over x, and limit as x goes to 0, cos x minus 1 over x. Do you remember what these guys are?
The sine one is 1, and then the cosine one is 0.
Yeah, good. All right. So for all of the problems kind of like this, we have to use some combination of these things. So if I want here, lim t to 0, tangent of 10t divided by the sine of 2t. The trick is going to be to split this up somehow into pieces that look like this. So my first move would be to rewrite this as sine 10t over cos 10t divided by sine of 2t. And then to kind of start breaking things up. So this is lim t goes to 0, sine 10t over 1 times 1 over cos 10t times 1 over sine of 2t, like this. So sort of each piece I just treat it on its own. The cos of 10t piece, this is easy. As t goes to 0, this is going to become the cosine of 0, which is 1. I know sine x over x goes to 1, so what I'd like to do is get a t down here. And I can do that by also putting a t up here. So basically, I'm going to take this and I'm going to multiply by t over t. One of those I'm going to put here. The other one I'm going to put over here. So everything here is being multiplied, so I can push pieces wherever I want them. This will give me lim t to 0, sine of 10t over t times 1 over cos of 10t times t over sine of 2t.
How are you allowed to choose where they go?
Well, it's just kind of how fractions multiply, right? A over b times c over d times e over f. I can rearrange these pieces however I want, because this is really just a times c times e over b times d times f. So I can pull this apart and break it up however I want it. I could call this c over b times e over d times a over f if I wanted to. So because these are being multiplied and these are being multiplied, and I can flip the order of multiplication around however I want, the upshot is that, yeah, you can, as long as all the fractions are being multiplied, you can kind of shove any one piece anywhere you want.
Okay.
Now we're almost to where where I want to be. The catch here is that this guy, remember, I want to use the fact that sine x over x goes to 1. So if this was sine 10t over 10t, that would go to 1, because that's like sine x over x. So the last thing I'm going to do here, sorry, there's a garbage truck right outside my window. Last thing I'm going to do here is multiply by a 10 down here. I can do that as long as I also multiply by a 10 up here. Right, like I'm multiplying by 10 over 10, and then I shove one of those 10s down here. And then I still have this piece, this 1 over cos of 10t, but I'm not really worried about him because we know he's going to go to 1. And then here, I want this to be a 2t to match the sine of 2t down there. So I'll say, okay, this is 2t over the sine of 2t, but I need to have something to cancel that 2 to make it equal to this. So where we end up with here, I can then give the limit to each piece. I'll have lim t to 0 sine of 10t over 10t times 10 over 1 times limit t to 0, 1 over the cosine of 10t times limit t to 0, 2t over the sine of 2t times 1/2. And each of these pieces I now know more or less how to handle. The way the book teaches this is they say you're going to make a substitution in this first guy. Here we're going to let x be 10t. And we're going to make a substitution in this guy. We're going to let x be, I should use a different letter, let y be 2t.
Are you allowed to separate it into the separate limits like earlier on?
You can, yep, you could do this at any step you wanted. I wouldn't do it any earlier than this because we really want to get these t's involved. So this step where we introduce those t's, that would be the earliest I would consider doing it. You could pull this guy out, the 1 over cos 10t at any point. He's not really consequential. But these other guys, yeah, you can split them up at whatever step you like. So now as t goes to 0, x is also going to go to 0, right? 10 times 0 is 0. So this piece becomes limit x goes to 0, sine of 10t, well 10t is x. So this is sine x over 10t again, that's x. And then I have 10 over 1. This piece, I'll just go ahead and say what this is, right? This is 1 over the cosine of 0. He doesn't have any issues at 0. This piece, when I make that substitution, I'll get lim, again, just like as t goes to 0, x goes to 0 here. If I plug in 0 for t, y is 2 times 0, that's also 0. So this is limit y to 0, y over sine of y times 1/2. So now we look at these and we ask, do I know what the pieces do? Again, the middle piece is just 1, not worried about that. Lim x to 0, sine x over x. This guy is 1. So from this first piece, I'll have 1 times 10 over 1. This piece, the cosine of 0 is 1, so this is just 1 over 1. And then over here, this piece is a little bit interesting. This is lim y to 0. I see y over sine y. So what I can do is I can actually flip this over. I can call it sine y over y to the negative first, kind of a sneaky trick, times 1/2. And now this piece, I recognize the limit as y goes to 0 of sine y over y is also 1. So right here I have a 10. Here I have a 1. And over here I have a 1 times 1/2. So at the end of the day, this is going to be 10 times 1/2 or 5. I think this particular problem is complicated in that it's asking you to do quite a bit. So it would probably be nice if this feels a little bit weird to solve a simpler version before going whole hog with this thing. But this is the procedure. And maybe a simpler one to practice with, we can come back to this in a second, but a simpler one I would advise practicing with is just something like, lim x to 0 sine 3x over 2x. Just something like this, where again, we're going to use the sine x over x special limit, but we need to do a little bit of symbol juggling. I really want this to be sine 3x over 3x. So what I'm going to do is multiply by 3 over 3. And then I'll just swap the 2 and the 3 here, right? This is, if we want to be really careful about it, this is lim x to 0 sine 3x over 6 x times 3 over 1. And then that's lim x to 0 sine 3x over 3x times 3 over 2. And now I can make the substitution like, y equals 3x, and this will become lim y to 0 sine y over y times 3/2. And we recognize this piece as being 1. So this is just 1 times 3/2 or 3/2. So this is kind of the thing that's going on in 2 different places in that other problem. And it is a tricky thing. How does this one feel?
A little better, definitely.
All right. So try running through this. See if you can kind of reason your way through this on your own. If you get stuck, come back and look at these steps. Maybe consider taking a screenshot or something, and then I can put the steps for the other problem back over here, and you can screenshot those to use them to guide yourself through if you get stuck.
Okay, I wrote them all down.
Okay, cool. And you got everything from this guy?
Yes.
All right, sweet. I'm going to bounce over to Alexander then, and then I'll come back to you if you had anything else you wanted to look at.
Okay.
All right. Alexander, what can I do for you, bud?
I was struggling on number 5 from the latest Calc 2 homework.
Let me see.
I think I'm struggling mostly with like definite integrals, like just moving the x's into thetas for the bounds, and then I think from there I might be okay.
All right, let me get this thing to load and we'll take a look. You said number 5, this one?
Yeah.
All right, let's do it. So we want to integrate from 2 to 6 dx over x squared minus 1 to the 3/2. Okay. So because this is like x squared minus a squared, I know I'm going to substitute for secant, right?
Yeah.
So this would be x equals a is 1. So the substitution is just x equals secant theta, which means my dx is going to be secant theta tangent theta d theta. And I also need to change my bounds. So my old lower bound is 2. My old upper bound is 6. When x is equal to 2, we have 2 equals secant theta, which is equivalent to saying 1/2 is equal to cos theta, which is equivalent to saying, or mostly equivalent to saying, theta is the inverse cosine of 1/2.
Which should be pi over 3, yeah?
Yes, pi over 3. So when x is 2, theta is pi over 3. Unfortunately, the inverse cosine of 1/6 is not as nice, but you can see that that's what we'll have for the other one. When x is equal to 6, we have 6 equals secant theta, which is equivalent to saying 1/6 is equal to cos theta, which is equivalent to saying theta is the inverse cosine of 1/6. So we just have to leave it like that.
Because there isn't a known value for that, yeah?
I mean, there is, but it's not one that we know from the unit circle. Like, it's not one that we would have memorized. So certainly this number exists, but it's hard to calculate, and it's not one that you would know off the top of your head. So we'd just leave it as the inverse cos of 1/6. Or if you wanted to leave it as the inverse secant of 6, that would be okay too.
That's pretty disgusting.
It is, yeah. Sometimes life is just like this. In any case, what we end up with is the integral from pi over 3 up to the inverse cosine of 1/6 of dx, which is secant theta, tangent theta. I'll put the d theta at the end. And then downstairs, I'll have secant squared theta minus 1 to the 3/2. And there's my d theta. I agree that those bounds are nasty. Sometimes we just have to deal with it though. There are some fun problems. If you look at the completing the square review that I have in the modules, I think there's a pretty gnarly example like this where you have to use like an inverse secant of something as a variable. It's nasty, but this happens sometimes. We just got to be brave.
So this would end up turning into secant theta, tan theta, d theta over tan to the 6th theta?
Something like that. Let's see exactly what we get. Definitely the top here is secant tangent. Downstairs, I'll have this piece is tan squared, right? Secant squared minus 1 is tan squared. So I'll have tan squared theta to the power of 3/2.
So it's just tan to the 3rd, yeah?
Yeah, it'll be tan cubed. Yep. So this is integral pi over 3 up to the inverse cosine of 1/6 secant tangent divided by tangent cubed. So the secant will live, the tangent will die, and I'll have 2 tangents downstairs. So this becomes integral from pi over 3 to the inverse cos of 1/6 secant theta over tan squared theta d theta. And I would look for a second at this stage to see if I see an obvious U substitution or anything nice. I don't, at least not immediately. So I start thinking, okay, let's rewrite as sines and cosines. From here, secant is 1 over cosine. And if I want to divide by tangent squared, that's the same as multiplying by cos squared over sine squared. So I would write it like this. And we'll see that a cosine cancels. And I get cosine over sine squared, right?
Yeah, I'm following.
And this isn't too bad because I can rewrite this as cosecant cotangent. Right?
Which is just negative cosecant.
Yeah, so the 1 over sine is cosecant theta. And the cos over sine is cotangent theta. So my antiderivative is going to be negative cosecant theta. And I'll have to evaluate this between pi over 3 and the inverse cosine of 1/6. Now the cosecant of the inverse cosine of 1/6 looks shitty, but it can be managed. First, I'd pop out the negative and then just write things down. Cosecant of inverse cos of 1/6. All right, that's scary. Minus the cosecant of 1/3, or sorry, cosecant of pi over 3. Second piece can be managed directly. The sine of pi over 3 is the square root of 3 over 2. So the cosecant of pi over 3 is 2 over the square root of 3. All right, I can make a note on the side here. Sine pi over 3, we know from the unit circle, is root 3 over 2.
Would you have to flip your bounds because you have the negative in the front?
No, I can just leave the negative out front. That negative came when I took the antiderivative, so it's not really a natural thing to say I'm going to flip the bounds of the integral. It will have that effect. It's going to make the first term here negative and the second term here positive. You could if you wanted to, but I think it's a little bit jarring to a reader. So I would probably just factor the negative out like this and then deal with it later. But if you wanted to handle it that way, you could. From here, I have negative cosecant. I'll just distribute the negative inverse cos of 1/6. And then minus minus will make plus 2 over the square root of 3. And then to handle this piece, we got to draw a triangle. So what I would do is use some letter. I can call it theta. I'm going to use phi here because we're using theta to mean something else. Let phi be the inverse cosine of 1/6. Then it follows that the cosine of phi is 1/6, which I am free to interpret as an adjacent over an hypotenuse. And then I can draw a little triangle in here. My adjacent side is 1. My hypotenuse is 6. So this side, this squared plus this squared equals this squared. So this guy is the square root of 6 squared minus 1 squared, or the square root of 35. So now what I'm after, remember, is the cosecant of the inverse cosine of 1/6. Well, the inverse cosine of 1/6, that is this angle phi. So I can look over to my triangle and say, okay, what is the cosecant of phi? Well, it should be the reciprocal of the sine of phi. The sine of phi is root 35 over 6.
So 6 over root 35.
Yeah, so this is going to be negative, I'll write it in orange, 6 over the square root of 35, because it's coming from the triangle there. And then we've got plus the 2 over root 3 from earlier. And that's it, you're done.
I kind of got lost as soon as the triangle came about. That's where I'm struggling here.
So take a look at this guy. Just don't worry about the specifics. Just look at the shape of it. Trig function of inverse trig function of number. Now let me direct your attention over to the modules. If we come into the review section on inverse trig here, trig function of inverse trig function of number, right? These sort of problems, 5, 6, and 7, these would be good to practice a little bit.
Okay.
So we can grind these out. Now the particulars that they've given you here are, they're too simple. Yeah, this can actually suck my whole ass. Yeah, there's nothing hard enough there to really get you the thing we need. Where is this business with drawing triangles? Trig, algebra trig review, inverse trig function, song trig equations. Let me see what we get. Let's see, where could I even search for this? Here we go. Patrick JMT to the rescue, like always. Let me see, is he going to help us with? Yeah, so this, simplifying these expressions using right triangles, you see he's doing exactly what we did. We want the tangent of the inverse sine of x. He calls the inside thing, the inverse trig function, theta. So theta is inverse sine of x. Then he says, okay, well that means sine of theta is equal to x. That's the line that's covered up by his hand right now. And he thinks of that as an opposite over hypotenuse and then draws a triangle. So for that sort of stuff, consider looking at some of these. I will paste them into chat. What else did we see here? This is a Beamer presentation. These are slides with lots of uncovering. That's not really good for what we're doing. Yeah, this ain't bad. This actually ain't bad. Cos squared of arctan of x, cotangent of arctan of x squared. These are okay too. So I would check these things out. They'd be good review. Maybe just watch that Patrick JMT video and then pick 1 or 2 examples here to look at. It'll help. There's plenty of things that you can practice with down here.
Sounds good. Thank you.
Of course, you're welcome. I think Robert popped in while we were doing this, and then Kaylee. So Robert, what can I do for you?
I had just a quick question about something. I just went and looked at the study guide for Calculus 1. I don't think that's the correct study guide.
Oh, let me see. So I published Calc 1 and Calc 2s. Maybe I got them swapped.
Yeah, because it was like, that doesn't look like anything else.
Doesn't look like the shit you guys have been doing.
No.
All right. Shit. Let me see. Yep. Nope. Sorry. This is Calc 2.
Yeah, I thought so. Like,
I'm so sorry. Yeah. Don't panic. Don't panic. I'll get rid of these. That's
okay.
my bad. All right.
I
Here.
just want to give you a heads up before the
Schedule, unschedule. So sorry about this. Yeah. I'll have to make an announcement on Canvas. I'm sure there's other people who are frightened by that. That is, what the hell is all of this? Please don't test me on this stuff.
At least not yet.
No, I'll get you on that next semester, but for now you're safe.
I think that was the only real question I had.
Oh, okay. Homework's going all right? Nothing else you want to look at?
I gotta get a little bit deeper into it, but maybe tomorrow.
Okay. All right. No stress then. I think, let's see. I think Kaylee and then Ethan. I think Ethan was our most recent entry, so Kaylee's probably next. What can I do for you, Kaylee?
Okay, so that's actually kind of like the question you were just doing with him was what I was gonna ask you with because I knew we were gonna have to do like secant inverse basically.
Mhm.
So like, you know how like if you go to the question you were doing with him, when you change the definite integral bounds, like you flipped it and then you did cosine inverse. Like,
Yes.
can you just leave it and then do secant inverse?
You can. Yep.
But like the thing is like I'm assuming we would have to know secant inverse because we didn't do that in trig.
So
Is that
the
why you
inverse
flipped it?
secant function, it works the same way as the others, but I wrote it in terms of the inverse cosine because I think most of you are more comfy with it. So it's up to you, but the inverse secant function does work the same way that the inverse, other inverse trig functions work. There's one small catch, and that's that the domain restriction isn't as well sorted as the domain restrictions for the other guys. So like inverse sine, inverse cosine, inverse tangent, everybody agrees that the restriction is negative pi over 2 to pi over 2 for sine, 0 to pi for cosine, negative pi over 2 to pi over 2 for tangent. But the inverse secant function, some folks disagree, right? You see here there's two options
Mhm.
and corresponding values of radians. And really you can work with either of these simultaneously, but the general thing that you'll find people doing is assuming that the x's inside the inverse secant function are greater than 1, and then the angles that the inverse secant function outputs are between 0 and pi over 2. This is sort of the standard assumption here, but there are other ways to do this. So I would prefer to work primarily in terms of inverse sine, cosine, and tangent. Anytime I find myself writing down the inverse secant of something, I ask, am I so attached to the secant function that I don't want to work with cosine instead? And the answer there is generally no.
Okay. So basically recommend that we just flip it and do cosine.
Yeah, so if I know, for example, that I needed to solve the equation secant theta equals 6, my very first step would be to say, all right, this is the same as saying, well, I would just say it like this. I would just say that the cos of theta is then 1/6. Right? These are equivalent. And this is, if you really want to get into the steps here, this is because secant is 1 over cosine. So this is the same as saying 1 over cos equals 6. And then you can say, okay, that's the same as saying 1 equals 6 cos theta. And that's the same as saying 1/6 equals cos theta, and then take the inverse cosine of both sides. But normally I would go from here to here, and then from here to here.
Okay.
But kind of the chain of logic is this, if you want it all.
Yeah, let me take a picture of it.
Sure.
Like the way whenever she would do that, she would just do like she would just be like, okay, so since you're doing the reciprocal of 1/6, what's the reciprocal of secant? She'll just do 1/secant. She's like, well, 1/secant is cosine, so that's how she would get it. So it's kind of funny, like
That
everyone
works.
looks at it
Yep.
different. Yeah.
Yeah, however you get from here to here, taking reciprocals from this line would get us to here. If you wanted to think of it like that, that works too.
So okay, so basically just whenever we have to do secant inverse, do cosine, like flip it and do cosine inverse. Okay.
Yeah, so there's an underlying identity here, and that's that the inverse secant of x is the same as the inverse cosine of 1 over x. So if I need the inverse secant of 6, like we did here, that's the same as the inverse cosine of 1/6.
Okay. And for what I was gonna say. That's a bad memory. Oh yeah, okay, so like should we know secant inverse and stuff like that? Like if we don't know it, should we like try to know it?
I would say that at the very least you should be comfortable with the definition of the inverse secant function. So we say the inverse secant of x is equal to theta means that the secant of theta is equal to x, and then you normally here you have a domain restriction for the theta values. 0 is less than or equal to theta is less than pi over 2, or what is the other one? Pi over 2 is less than theta is less than pi. I think this is the 0 is less than pi over 2. Yep, pi over 2 is less than pi. So the idea is, you remember where all this stuff comes from is that when we go to invert the trig functions, they're not one-to-one.
Mm-hmm. So you gotta pick like a specific part of it.
And if I look at, so if I look at the graph of the secant function, I'll say here's pi over 2, here's pi, here's 3 pi over 2, here's 2 pi, here's negative pi over 2, here's negative pi, negative 3 pi over 2, and negative 2 pi. Secant has these vertical asymptotes at odd multiples of pi over 2. Just like tangent, and then within each of these pieces, he has kind of this shape. And then down here, so this is 1, this would be negative 1. And then he's back up here. And with the tangent function, we can say, I'm just going to take the stuff from negative pi over 2 to pi over 2. And because that is 1-to-1, I'll invert my function there. But unfortunately, the secant function isn't 1-to-1 there, right? He runs into trouble there. So when you choose to restrict the graph of the secant function, right, this is my theta axis, I can't like just take this piece because this piece isn't 1-to-1. It doesn't pass the horizontal line test. But I can say I'm going to take like the piece from here to here. So when I think of my secant function as being like inverted, I take this piece and this piece. That's sort of the standard way to do it. But some people do it a little differently. Some people take this piece and this piece, which I think is a little weird because you've got like a big gap in between. But yeah, this is normally what we think of as the restricted domain secant function who does have an inverse.
So is that why they say 0 to pi over 2 or pi over 2 to pi, because that the asymptote?
Right, yeah, we have to chop pi over 2 itself out. So 0 to pi over 2 is right here. Here's the closed, left closed, right open interval 0 to pi over 2. 0 is less than or equal to theta is less than pi over 2. And then here is the left open, right closed interval pi over 2 to pi, which is this second piece.
Okay. So, sorry. So should we also, I'm assuming we should also know cosecant and cotangent inverse.
So again, but in practice, what we really need to get shit done are sine, cosine, and tangent. If you got those three, you're good. Because anything that I need to do with the inverse secant function, I can shoehorn in using the inverse cosine function. Same is true of cosecant and cotangent. Anything I need to do with the cosecant function, I can sneak my way in with the inverse sine. Anything I need to do with the inverse cotangent function, I can sneak my way in with the inverse tangent function. So I wouldn't stress too much. Like if you're trying to budget your time and figure out where to put your energy, I would focus on sine, cosine, and tangent. Don't worry so much about secant, cosecant, cotangent, because anything we need to do with those, we can do with sine, cosine, and tangent.
Okay.
But inverse
I just wanted to know.
shows up enough that it's worth at least knowing.
Okay, so I'll try to look at that a little bit, but yeah, because I didn't we didn't learn the inverse of the other three. We just learned the inverse of the first three.
Yeah, and that's understandable. That's pretty normal. We don't really stress a whole lot on those because they can be done in terms of the others. But certainly you can define them. They do exist. And if you want to, the Wikipedia page is pretty good. You can talk a little bit about, the associated domains and ranges. They should even have some graphs here somewhere. I hope. Yeah, here we go. So sine and arcsine, these we should know. Cosine and inverse cosine, we should know. Tangent and arctangent, we should know. They have the graph here of secant and the inverse secant, but it doesn't look like.
Yeah, I've seen it before. It looked a little weird.
They're strange. Even this Wikipedia page doesn't have the inverse cosecant or inverse cotangent function graphed, which is okay because we don't use them a lot.
Okay.
So focus
All right.
on
Well, thank you.
sine,
I was like wondering. Okay.
no worries.
I knew for the definite we were gonna have to do like secant inverse, and I was like, how do we do that? And then I walked in, you guys were doing that question. So.
Yep. Yeah, I would just do it like this. Just do it in terms of the cosine function.
Okay. All right. Thank you.
You're welcome. I think that's Ethan's turn then.
Yo, I'm trying to dig my way out of the calculus hole because I fell behind in the last lesson.
Okay.
So I'm pretty much just trying to focus on this that lesson / chapter before we move on a little further in Thursday's class. So if you have access to like the previous homework, I think one that is making me struggle is 21, where it has you do a it has you do a trig interval, but also reflected or rotated around the x-axis, which is really tripping me out.
All right. So that's this guy, right?
Yeah, that's it.
All right. So the graph of sine squared isn't a graph that's like immediately obvious, but it turns out to look kind of like the sine function, just, how do I say this? So if you square something, it's going to be made positive, right?
Yeah.
So let me call this, we're going from 0 to pi. Let me call this 2 pi. That makes this pi, and that makes this pi over 2. Normally the sine function would go like 0 to up to 1 at pi over 2 and then back to 0 at pi, right? And it would turn around. Sine squared kind of does something a little bit funny. So if this is going to be y equals 3 sine squared of x, rather than crossing through 0 at pi, it's going to bounce off 0.
Okay.
But it will still come up to its max here at pi over 2. And so we're going to...
If you're drawing the graph, I cannot see it.
Oh, shit. Sorry. Yeah.
It's all good.
So
Hey, there it is.
crossing at pi, we're going to bounce at pi. We're still going to turn around and have our max there. So the graph of our sine squared function should look something. And then again, instead of crossing at 0, we're going to bounce at 0, something like this, modulo my shitty art skills. And then it's going to do the same sort of thing, 3 pi over 2, where sine is normally down here at its negative max. He'll come up here, and then he'll kind of roll around again. So something like this, what sine squared
Okay.
looks like. I want to rotate this region from 0 to pi about the x-axis, it says, right?
Yeah.
Okay. So this is my axis of rotation. My region is all this shit in here. And I have a choice of methods, right? I can use the disk washer method or the cylindrical shells method.
It's probably simpler just to use the dishwasher method.
For sure, much simpler. Why?
Because doing the cylindrical shells method would require you to put that function into terms of y, which would be a little bit of a bitch to do with this.
Yeah, literally impossible, right? It's not one-to-one.
Oh, really?
Yeah, I mean, you could exploit a symmetry here. So this function is invertible from 0 to pi over 2 because this portion is 1-to-1. So you could, in theory, do it like that and then double. But yeah, your right minus left, you would never be able to figure it out because this right thing can't be written cleanly as a function of y. So you're exactly correct and for the right reasons, which is awesome. So we're going to use the disk washer method, which means my strip needs to be drawn perpendicular to the axis of rotation. Like here.
Yeah, and theoretically, with the knowledge I had, I could have done this problem, but I was so burnt out by the time I got to it that I had to shelve it.
Don't feel bad. Don't feel bad. That's what office hours are for. I'm here to unburn you out. So I need to cook up a few things, right? If I rotate just that object, I'll get a disk. There's no inner gap here because there is no gap between my axis of rotation and the bottom end of my strip. So if I rotated just that little slice, I would get something looking like this, right? And this bad boy has a radius. Which is the thing I've been calling capital R in the lectures, like the outer radius. It has a little differential thickness, which is dx, because my strip's a vertical strip, so its thickness is a tiny little x step. And so
Okay, and so big R would be 3 pi cubed of x, right? Or would it just be 1?
Not quite. So let's characterize the point up here. This is what I was going to do a second ago. This point along the graph is like x comma 3 sine squared x, right? Because the point along the graph y equals f of x is always x comma f of x. So the radius r is the distance from the far end of the strip to the axis of rotation. So that's this.
Okay.
Which is the y value here minus the y value down here. So r is 3 sine squared x minus 0, because the y value down here is 0.
Mhm.
Cool.
Okay.
And now we're ready to rock.
Yeah, I think I misspoke when I talked about it. I called it like a cubed sign when it was actually just squared.
Yeah, okay, yeah, that's correct then. Yep, just 3 sine squared x. So then dv, which is normally pi times big R squared minus little r squared times your differential. Little r here is 0, right? There is no gap. between the near end of strip and the axis of rotation. So this dv is pi times 3 sine squared of x all squared dx. Right, I'm not even, this guy right here, he's nothing. And big R is just 3 sine squared x. So when I square that, I'll get pi times 9 sine to the 4 of x dx, which is not the most fun thing in the world to integrate, but we can do it.
Okay, and so the integration of that would be, I just put the pi and the sine in front of the integration symbol, but it would be sine to 5 of x over 5 times 1 over cosine of x. Would that be true?
I got to think about this a little bit more. So
It's all good.
first, my bounds of integration are going to be from 0 to pi. And then I'll have the 4th power of sine x dx. Now, it sounds like you're trying to use a kind of power rule on this, right? Like bumping that
Yes.
power up by 1. We can't do that, unfortunately.
Ah,
If I had like a cos x floating around here and I could substitute for sine x, then I could do that.
well, the way that I was thinking is that technically you could just multiply it by cosine x over cosine x, and then you'd just be left with a 1 over cosine.
But then what do I do with that 1 over cosine in my integral? Yeah. If that was a constant, then I could pop the 1 over cosine out and maybe like make it go through like that.
Okay.
But unfortunately, the way I would like when I see this, what I think is, I have sine to the 4 and cos to the 0. So both of the powers are even. So my strategy tells me what to do. I'm gonna have to grind away with half angle identities.
Ah, I see.
Okay, I'm getting a call here from a number I don't recognize. Let me make sure this is
No problem.
Hello? Hello? Fuck y'all. All right. So yeah, unfortunately, this is like a 7.2 integral. Of the form integral sine mx cos nx dx, where m is equal to 4 and n is equal to 0. Both powers are even. So we use half angles. We use the identities cos squared equals 1/2 1 plus cos 2x, or sine squared equals 1/2 1 minus cos 2x. And we're going to use these until we've broken this down into something we know how to take an integral of like right away. Unfortunately, because the power here is 4, it means we're going to have to do quite a bit of this, but we'll get through it.
Could you just split it up into sine squared of x multiplied by sine squared of x, and then just use the double angle theorem on those guys? Or
That's
how does
exactly
that
it. Yep,
Okay.
That's precisely what we do. So that will be 9 pi integral 0 to pi 1/2 1 minus cos, and I'm going to be careful with my parentheses here. I was sloppy here, but over here I'm going to be careful, like this, times the same thing, 1/2 1 minus cos 2x, like this, dx. So the two 1/2s, these are constant multiples. They can both come out as a 1/4. So I'll have 9 pi over 4 times the integral from 0 to pi, 1 minus cos 2x times 1 minus cos 2x dx. And now we FOIL, cross our fingers, blah, blah, blah. Let's see. So that's 9 pi over 4 integral 0 to pi 1 minus 2 cosine 2x plus cosine squared of 2x dx, like this. And our objective with these sort of integrals where the powers are both even, the sine cosine integrals where both of the powers are even, the objective is to get rid of all the powers by repeatedly applying these identities. So what I see here is a cos squared of 2x, which is a cos squared of something. So I have to use
So-
a modified form of this.
Okay. Can we just isolate that as its own integral instead and make things a little easier?
You could, but it's actually going to throw out another term that can be combined with this one. So I
Oh, okay.
leave everything together for now. I would say if cos squared of x is 1/2 1 plus cos 2x, then cos squared of 2x should be 1/2 times 1 plus the cos of 4x. What matters is that the inside of the trig function on the right is double the inside of the trig function on the left. So this piece I'll replace by this thing. It can be easier to see if we step to the side for a minute and think about it. And if I rewrite these identities using a different variable, so let me write it like this: cos squared of theta equals 1/2 1 plus cos of 2 theta. Then if I plug theta equals x, I get the normal one, right? Cos squared of x equals 1/2 1 plus cos 2x. Or if I plug theta equals 2x, then this would be cos squared of 2x. And over here I'll have 1/2 times 1 plus the cosine of 2 times 2x, which is the cosine of 4x.
Okay.
This is a kind of weird thing, but it works. We call them half angle identities because the angle on the left is half of the angle on the right. So over here, I've got cos squared of x, which is half of 2x. So if I want this to be a 2x, this would be a 4x. If I want this to be a 6x, this would be a 12x. Anything
Exactly.
like that will work. So we come back here. I have 9 pi over 4, integral 0 to pi, 1 minus 2 cos 2x plus 1/2 times 1 plus cos 4x dx, like this.
All right. Can I take just a minute to see that?
Sure,
Let's see.
sure.
Okay. I see.
So now I'll distribute the 1/2. This is going to go here and also here. The 1/2 times the 1 is going to give me something I can put together with this. It's going to give me a constant. The 1/2 times cos 4x is manageable on its own. So let's see where we land. Make some space here. We will get 9 pi over 4 integral 0 to pi 1 minus 2 cosine of 2x plus 1/2 plus 1/2 cosine of 4x dx. And now this and this are like terms.
Yeah, so we just put them together.
Yep. And 1 plus 1/2, that's 3/2. So this is 3/2 minus 2 cosine of 2x plus 1/2 cosine of 4x dx. Yeah, I'll have 1 hour between this and the next thing. All right, so now I know how to integrate a constant. I know how to integrate cos 2x, and I know how to integrate cos 4x. So from here, we're actually groovy.
Yeah.
We're good. So this is going to be.
Also, if you have something you need to attend to, like this is just basic integration, like I can totally sort it out from here.
Let's get our antiderivative and then we'll call it a day, all right?
All right, dope.
So the 3/2 is going to become 3/2 x. Cos 2x, his antiderivative is sine 2x over 2. That's a micro u sub, right?
Mm-hmm.
So the 2 here will cancel. I'll write it out. This is 2 sine 2x over 2, and you can cancel the 2's. And then here, this is another micro u sub. So cos 4x will integrate to sine 4x over 4. And this 1/2 is going to make that sine 4x over 8. And this is what we evaluate from 0 to pi. And the sad truth about many of these integrals is that all the work we did to get these terms ain't gonna
Doesn't
get
really
shit.
matter.
Yeah, they
Yeah.
don't. Everything comes from this. But that's it. And if the bounds were different, you know, we would get something from them. But that's all. So we'll just evaluate this chunk between 0 and pi. You should get something like 27 pi squared over 8, I think. Something like
Yeah. Because it's just the 3/2 x because sine doesn't operate at pi or 0.
Yep.
But yeah,
these
thank
pieces
you
are
for
both
helping me
0
sort
there.
that out.
You're welcome. You're welcome, Ethan. All right, I got to get running, but I will see you next time.
All right, have a great day, Professor. I'll see you tomorrow.
Take care. Take care.
Bye-bye.